Welcome back, everyone. This is Earth and Space Science 101. This is lecture 23. So we're continuing through our chronology of Earth history. We went through the basics of the geologic timescale in the last lecture. So if any of these terms mix you up, just go back and reference the stuff from the beginning of that last lecture as far as how we break down units of time, how we break down time into eons and eras and so on. So in addition to that, in the last lecture, we also covered the Hadean eon, that first 500 million years of Earth history, where all that really integral stuff happened. We got the moon, we got an atmosphere, we obtained our oceans by the end of the Hadean. And so increasingly, more and more, Earth is actually starting to look somewhat similar to our planet today. Now, the big obvious difference is our planet is covered in life today, whereas there is essentially no Earth, no life at the very end of the Hadean. There are going to be some other notable differences, mainly because we don't have really a working plate tectonic cycle yet, and we don't have oxygen in the atmosphere. So it's somewhat like Earth, but a very weird early version of Earth. That's where we're going to start off in the beginning of the next eon of geologic time. And that's called the Archean. Okay, so the eons of geologic time, to recap from last time, are the Hadean, the Archean, the Proterozoic, and the Phanerozoic. Last time we covered the Hadean. Today it's the Archean and the Proterozoic. So we're going through the rest of the Precambrian eons. This sort of circular version of the geologic timescale should help sort of jog your memory a little bit. We're going back through the sort of purple chunk of time here to the beginning of the Archean, and then from this time all the way up to present, we're going to have some of these forms of life, some of these very, very primitive forms of life around on Earth. This is mainly going to go back to very, very primitive life, including stuff like bacterial life, some of the earliest primitive bacterial life that are going to be in the domain of life called archaea. So a little bit more on that later. But for now, just remember that the Precambrian is going to break down into the Hadean, where we have very little actual record, but we have all of these events that we know must have occurred at some point during that period of time, like the formation of the oceans, the atmosphere, and the moon. In the Archean and the Proterozoic, we end up having much better records than we did for the Hadean, because we have actual rock preserved from this time. So we're going to start to see the very beginning of life during the Archean. We're going to see the oceans that are newly formed, being this place where life is going to begin and thrive. And we're even going to see the beginning of the continents and the beginning of the plate tectonic cycle. It's all going to start during this period of time. Towards the end of the Archean and the beginning of the Proterozoic, we'll even see oxygen start to become abundant in the Earth's atmosphere, and that's going to be a very, very important part of the story. So we'll start with what's going on with plate tectonics during this time, what's going on with the actual physical geology on Earth. So prior to this time, remember that the Earth's surface was so hot that you didn't actually have brittle plates like we have in plate tectonics today. And these plates weren't really moving around and doing things like creating mountains and ocean basins and earthquakes and all this kind of stuff, because the rock itself is just too hot. It can't behave brittly until temperatures cool down substantially. So once you get into the Archean, you have temperatures actually cool down to the point where the plate tectonic cycle can really start. And with the start of the plate tectonic cycle, you're going to have the start of the world's first true continents. Now, there's certainly the possibility that prior to this, you had some of these volcanic island arcs, so it wasn't completely a water world with no land masses at all, but you don't really have stable continents yet until you get partway through the Archean period. Our oldest rock on Earth is actually some of this residual continental crust. So in this the Archean crust, it basically breaks down into oceanic crust, where there's really no record of that still existing today, but there would have been a substantial amount of oceanic crust and island arc volcanics. These volcanics would have been these things called volcanic komatiites. It's a very particular type of volcanic eruption that occurs when you have much higher temperatures and pressures in the early Earth than we really do today. So we don't really have many of these same types of eruptions as were occurring during the Archean eon. What we do still have remaining today in some very isolated locations, like in South Africa and in parts of the Rockies and Canada, are some of these residual continental land masses. These would have been the first early continents where all of the crust that we have today really sort of grew around. And then those continents would have started moving around the globe in accordance with plate tectonics. So these felsic granitoids is essentially sort of a fancy word for felsic rock that is granitic. And so this is going to be very lightweight rock that is not going to be subducted and not get back recycled into the mantle during plate tectonics. That's essentially the reason why it's still around today, and some of it's actually exposed to the Earth's surface, is because it's actually felsic rock. So if you remember back to our discussion on rocks and minerals, felsic rock is a little bit different than mafic rock in that it essentially has to evolve as some of these denser minerals are crystallizing out of a melt, and then that lighter material then continues to rise up towards the surface. So this is sort of the end result of Bowen's reaction series is essentially the formation of these first felsic continental land masses. And then we continue to have crust forming around these land masses today. So some of this earliest continental material, these felsic granitoids and these things called greenstone belts that form in the low areas of these continental crusts, those are still formed today. So, essentially what's happening here is we have a little bit of this continental land mass forming. So we have some shallow marine environments around these land masses. Unlike today, where shallow marine environments are really key and they're really thriving with regard to life, all of these oceans, all of these continents, all of the shallow marine environments around the continents, they would have been largely devoid of life because the pressures that existed within the Earth's atmospheres and the temperatures that existed in the water, in the oceans, and on the Earth's surface would have been far too hot to allow for life to form. We think the very earliest forms of life didn't form anywhere close to the surface of the oceans, or definitely not on the continents at all. They actually formed deep, deep, deep under the oceans, at the floor of the oceans, in these mid-ocean ridges that are still integral to the plate tectonic cycle today. Those are the divergent plate boundaries, the spreading centers in which all of this motion with plate tectonics is still going to be occurring today. So in these environments, you have a lot of hot water, a lot of various types of chemicals like carbon dioxide and sulfuric acid coming out of the crust itself at these mid-ocean ridges. And so these places are very key for the beginning of life because they allowed for a place for these very early organisms to actually set up some sort of a life process similar to how we breathe to continue our lives on the surface of the Earth today. Instead of breathing and using oxygen as a way of metabolizing and deriving energy, these organisms were chemosynthetic. So they broke down various types of chemicals like the carbon dioxide and the sulfuric gas and so on in order to derive energy from that process and to sustain their life and to have offspring. And so this is really sort of the very origin of life. And certainly the earliest fossil evidence of life exists in these same sort of environments. While the earliest fossil evidence of life goes back to about 3.8 million years ago, we think there's possibly some non-fossil, but essentially chemical evidence of early life dating back even earlier than that, possibly to 4 billion years ago, even possibly during some of the parts of the Hadean. So we can't put a number specifically on exactly when life began on Earth, but there's at least certainly fossil evidence for that life once you get into the early Archean period. So what I love about all of this, and what's really key here, is that life on Earth and the Earth itself are evolving together. They're growing and changing and becoming more interesting and more complex. All of that's happening together. And so while plate tectonics is originating on Earth, life is forming on Earth and finding a way to use that plate tectonics to derive energy by means of doing the chemosynthesis at these mid-ocean ridges. Now, I want to take a little moment and do a little bit of a biology speech here. You know, I'm certainly no biologist, but I want to get into a little bit of the differences between these earliest organisms, these early bacterial organisms, and some of the cells in your own body. So I call these earliest organisms prokaryotic organisms. And what this means is that they're single-cell organisms and they have the most basic cellular structure possible, a prokaryotic cellular structure. This means that there's basically a membrane surrounding the organism and then some DNA in there, and then not a whole lot else is going on here. Whereas comparatively, organisms like us, eukaryotic, multicellular organisms, have individual cells like the red blood cells in your body that are extremely complex. This most likely happened because of prokaryotic organisms absorbing other prokaryotic organisms and then evolving in a way that allowed for these eukaryotic organisms to actually become way more complex. So this is just one of the differences between some of these earliest organisms and then life on Earth today, is that these organisms would get far, far more complex. The earliest life on Earth is not going to be walking, talking, swimming, really very interesting organisms by our standards today. It's going to be extremely simple forms of life. But those simple forms of life are going to evolve and thrive, especially when the Earth is going to have climatic conditions that allow for this thriving to occur. So the other thing that I wanted to cover while I'm going through a little bit of biology here is the different forms of life. We are, of course, animals. We're mammals. We're within this domain of life called eukarya. And most of the life that you can really think of on Earth is going to be of this eukaryotic variety. Plants, fungus, even some types of bacteria are all going to be in domain eukarya. A lot of these earlier organisms, though, are not going to be eukaryotic organisms. They're not going to be in that domain at all. They're going to be in the bacteria domain, and a lot of them are actually going to be in the archaea domain. And that archaea has a term that should start to sort of sound familiar. That root ARCH always just means old. Right? So all of these are going to be what we call extremophiles today. They're going to be organisms that love extreme environments today because they don't have a lot of competition with other forms of life to thrive there, because they're really the only organisms that can thrive in that kind of situation. They're going to be organisms that thrive in really salty areas or very hot or very cold areas today. So when we look for the signs of life on other planets, like our search for life on Mars, or at least search for the possibility that there was ever life on Mars, we're not looking for eukaryotic life for the most part. We're not looking for anything of great complexity. We're mainly looking for the extremophile archaea types of life. So as we go through the archaea, the Archean eon, that's the things that I really want to solidify here, is that you have the beginning of the plate tectonic cycle, you have the origin of the first continents, and then you have the origin of life itself, even though this life is going to be extremely simple. Now the Earth and the life can continue to become more complex and can continue to become more interesting together. So that's going to take us through the Archean, and now we're going to arrive at the beginning of the Proterozoic. So the thing that really differentiates the Proterozoic is what life is going to do to the Earth's atmosphere, and what in turn those changes to the Earth's atmosphere are going to do for life. The thing that really defines the beginning of the Proterozoic is that oxygen is going to become abundant in the Earth's atmosphere. Of course, it wouldn't be possible for me to be giving this speech right now and talking and breathing and surviving without the oxygen being present in the Earth's atmosphere. And even most of the forms of life that are going to live in the oceans, they are still going to require oxygen. They're still breathing oxygen. That oxygen is just going to be dissolved into the oceans. So for anything bigger than a bacteria to form on your planet, you have to have oxygen. But the trick here is that oxygen is not part of the original package that a planet comes with. It just doesn't form on its own. You have to have early life on that planet to form that oxygen for the later forms of life to be able to use and appreciate, like I do, and certainly you do too. So the oxygen on our planet is going to form as a result of some of these organisms that are going to take over the shallow marine environments on Earth, the places that are surrounding the continents. This is going to be a blue-green algae that we'll talk about in a little bit more detail. Another thing that we're going to cover as we go through the Proterozoic, as we sort of do a speed run of the next 2 billion years here, is some of the changes that are going to occur with the continental land masses, how they're going to continue to grow, how continents are going to take over a little bit more of the globe. Oceans are always going to be more dominant and are still more dominant today, but there'll be more continental land masses by the end of the Proterozoic than we start with. And those continental land masses are going to do something very interesting by the end of the Proterozoic. So the first part of the story, the most important thing to discuss within the Proterozoic is, of course, the oxygen. The oxygen has to be the result of photosynthesis. Now, if you've ever taken a biology class, not even necessarily a college-level biology class, but even a high school biology class, you know the word photosynthesis. It's essentially what plants do. But before plants figured out how to do this, some of these earlier bacterial organisms were figuring out how to do this. So it was blue-green algae, which is actually a bacterial type of algae instead of a plant, in the early Proterozoic that started pumping oxygen into the atmosphere by undergoing photosynthesis. These algae produce these structures that get recorded very, very well in the rock record and provide us with some of the strongest evidence for this process undergoing in the early Proterozoic. These structures that the bacteria form are called stromatolites. So before I get into this a little bit more, I want to cut to a little bit of a field trip here that's going to show you some of these same organisms thriving on Earth today. So today's field trip is actually going to take us as far away from our current location as we have on any of our field trips that we've done this semester. This is also our last field trip, so we're going to make it a good one. We're going to go to the western coast of Australia to a small little place called Shark Bay. Now, the reason why we're going to Shark Bay is because this is one of the only locations in the world where you can find these sort of combination between this geologic and biological structure called a stromatolite. Stromatolites are only found in what we call hypersaline environments today. So Shark Bay is a place where you have saltier than normal conditions in the water. This is their sort of ecological niche today, but we think in the past, when there weren't large predators, when there was nothing that viewed the cyanobacteria really as prey, these structures were found all over the world. So we think that this is a really important modern analog to the way that most coastlines looked around about the time, about 2.5 billion years ago, that oxygen started to become present in the atmosphere. So these same cyanobacteria that build these stromatolites, they create this algal mat, and then that cyanobacteria creates the rock itself and creates the structure upward, really just as a waste product. They are also the first organisms that really figured out how to go through photosynthesis. So most of the oxygen in our atmosphere is there only because of the stromatolites. So through photosynthesis, they took this carbon dioxide out of the air, which then cooled global temperatures, and then they replaced it with oxygen, which allowed for larger forms of life to be present later on. So we really view Shark Bay as not just an important biological site, because it's really one of the only homes left for these cyanobacteria that create the stromatolites, but it's a really important geological site as well, because it gives us this analog and it gives us this idea of how coastlines looked in the past. And this organism was really important in forming most of the oxygen in the world today. All right, so that gives you a little bit of a taste of what these organisms look like today, and a little bit of an appreciation of how amazing these organisms are. These are organisms that are still around after 2.5 billion years on Earth. They might be restricted to some of the extreme environments that you saw in the video, but they're still around. They're still thriving. So if humans can do as well on Earth, it'd be pretty shocking. In the grand scheme of things, if we can be around for 2.5 billion years. So these organisms are a blue-green algae. If we looked at individual organisms, of course, we would have to be looking at them under a microscope. But to look at them in mass, all you have to do is look at these structures that they create. They create these bacterial mats and create the rock itself that makes these kind of bulbous structures that grow in hypersaline lagoons today. But without competition in the early Earth and the early Proterozoic, they would have surrounded the continents. They would have been everywhere. There's nothing to feast on them. There's no competition. So they could essentially just almost take over all of the shallow marine environments on Earth. So surrounding every single continent on Earth, it would have looked like Shark Bay today. You would have had all these bulbous structures. And the reason we know this is because those structures get recorded in the rock. We can see these stromatolitic structures. Now, the other thing that is a really great record of this time is what happens in the oceanic floor and what gets recorded later into rocks as a result of all of this oxygen coming into the system. So slowly, over hundreds of thousands and millions of years, these organisms are pumping out oxygen, and they're also filtering out the carbon dioxide. So the roughly 20% of the Earth's atmosphere that was composed of carbon dioxide and made temperatures really hot on Earth is now composed of oxygen. So prior to this, we would have had red skies on Earth, because it's just like on Mars. The red atmosphere of Mars is a result of the carbon dioxide in that atmosphere, and that's what makes it red. The same thing would have happened on Earth when our atmosphere had more carbon dioxide. So when the organisms took that carbon dioxide out and pumped in oxygen in its place, the atmosphere would have turned from red to blue. So the fact that we have blue skies today is a result of the oxygen in the atmosphere. The other thing that would have happened is that the oceans on Earth would have been green, like an olive, kind of murky green color prior to 2.5 billion years ago, because there was tons of iron dissolved into the oceans. Once you start to pump dissolved oxygen into the oceans by way of increasing this oxygen in the Earth's atmosphere and then slowly dissolving that into the oceans, the iron then has to rust out. And so most of the iron that we use today for really just about anything comes from these banded iron formations that formed at around this time. It's banded layers of iron oxides. It's essentially the rust that was all of this iron coming out of the ocean and being precipitated on the seafloor, layered with chert. So all of this silicon that's going to just form naturally on the ocean floor anyway. So now when these same deposits form on the ocean floor, because there's no more iron left in the ocean, you just have chert. But at this time, you have banded layers of chert and iron. And so these iron layers are, again, most of the iron that we use today. There's a lot of iron in things like mafic rock, even some felsic rocks contain some small amount of iron. There are iron sulfides on Earth. So there's lots of iron left behind in other deposits on Earth, but it's not very easily extractable from the rest of the matrix of that rock. In the case of these iron oxides and these banded iron formations, it's very easy to extract just the iron that you want and build everything that we need iron to build. Things like buildings, how you produce steel, how you produce all of these different metals originally requires having iron. And these irons are found predominantly in these banded iron formations. So a little bit of fun kind of play-by-play here is looking at the difference between this older car that's mainly iron. It's one of these big heavy tanks from the late 40s. It's a 49 Ford. It's formed predominantly from Proterozoic iron. Later cars have a lot more plastic, like this 81 Corvette. And plastics are, of course, a derivative of oil. So that plastic is coming from a completely different source. It's coming from the same source as most of our oil resources. So all of this oxygen is going to come into the oceans. It's going to dissolve out that rust. You're going to have to pour a certain amount of oxygen into the ocean to just dissolve out all the iron first before it's possible to you have organisms undergoing respiration and using this oxygen. And there are other chemical sinks for oxygen that has to be filled up, but eventually it can dissolve out into the oceans, and it can even fill out the atmosphere. And so millions of years later, you have an atmosphere that's composed of 20% oxygen. Later on, it's even possible for some of that oxygen to break down and to form this different version of oxygen that actually has 3 atoms of oxygen instead of just 2. If you have molecular, normal atmospheric oxygen, molecular oxygen, it's usually oxygen with 2 atoms. It's O2. That's the stuff that we're breathing. If you have a molecule that has 3 oxygens, that's called ozone. And ozone is predominantly going to reside in the upper part of the atmosphere known as the stratosphere and make the ozone layer. So all of these really, really important things are going to happen that are going to allow life to thrive later on Earth, including the formation of oxygen dissolved in the oceans, oxygen in the atmosphere, and the formation of the ozone layer that will eventually make it possible for organisms to conquer the land. So oxygen, again, is the really sort of important thing that's happening in this eon of time, and it's transforming the planet. To get a little bit of a visual on how this is going to so revolutionize the planet and transform the planet, I want to cut to, in this case, not a field trip, but a little segment of a video. I'd highly encourage you to watch this whole video if you have the opportunity to, but at least we're going to watch these couple of minutes right here. This is from the pilot of How the Earth Was Made, and it's going to show you what the oxygen in the atmosphere and in the oceans is going to do to really change the overall look of the planet.
The rock record shows that by 2.5 billion years ago, stromatolites were blossoming globally. All beaches on Earth would have resembled Shark Bay. And as stromatolites filled the shallows, they began to fill the atmosphere with oxygen.
Planet Earth in the solar system is the only planet that has an atmosphere composed of a large amount of oxygen. geoscientists think that that oxygen came only from the reaction of stromatolites.
The algae turned sunlight into oxygen, a process known as photosynthesis. Over a period of 2 billion years, countless generations of stromatolites pumped out over 20 billion tons of oxygen. At first, the gas dissolved into the oceans, where it rusted out billions of tons of iron. But eventually, it would also fill the atmosphere and transform the planet. The planet's very appearance was dramatically altered. As the iron left the oceans, they changed from green to blue. When the oxygen moved on to the atmosphere, it diluted the remaining thick carbon dioxide and cleared the air. After nearly 2 billion years of oxygenation, the blue planet was born. The Earth now had its blue oceans and its blue sky. Relics of this great transformative period survive today in immense layers of iron-rich sediment originally deposited on the floors of the ancient oceans. Scattered all throughout the globe, the banded iron formations, as they are known, are vital for today's economies. They are the major source of all the iron mined today.
So hopefully that gave you a little bit of an appreciation for how oxygen changes the entire appearance of the planet. So going to visit the early Earth in the Archean versus going to visit the early Earth midway through the Proterozoic, it would have looked like two completely different planets. And that's one of these things that I really like to stress when we talk about early Earth history. There are lots of video games and lots of science fiction where all of these different type of planets are going to be there. If you think about like maybe the Star Wars movies, there are desert planets and there's ice worlds, there are hell worlds, you know, there are planets that are covered in lava and, you know, they visit all of these different places. Earth, throughout its entire history, has really been all of these different places. It's been a hell world. It's been a water world. It's been a world without oxygen and then finally with oxygen. And the thing that we're going to see next is Earth turning into an ice world. So by midway through the Proterozoic, things are looking really great for life. Life is looking, like it has a really good footing on this planet. Life is even starting to get increasingly more complicated. And the overall evolution of life probably would have taken place a lot more rapidly were it not for this next event that would have set back the formation of life and the evolution of life significantly for hundreds of millions of years. Now, to set the stage for all of this, you have to remember that the plate tectonic cycle is still going on. We still have the formation of all of these continents. And up until this point, they're all isolated continents, much like we have today, where all of these continents are kind of spread out throughout the globe. What's going to happen next is that all of these continents are going to slowly inch their way towards this position where they're assembled as a supercontinent, much like Pangaea at the end of the Paleozoic. But this is a supercontinent that not many people have ever heard of. It's what's probably thought of as the world's first supercontinent, and this one is called Rodinia. Whereas Pangaea formed fairly close to the Earth's equator, Rodinia formed where all of these continents were all accumulated together as one big supercontinent near the South Pole. Now, for reasons that go back to some pretty complicated ocean current structures, this position of the supercontinent at the South Pole is going to be very, very detrimental to the climate on Earth because it essentially blocks water from going from the equator and reaching the South Pole. And this means that the South Pole could get very, very cold. And then when the seasons change, it means that the North Pole could get very, very cold. And so these rapid changes in climate seasonally were occurring on Earth. And then what happens is a tremendous amount of ice builds up on the poles, far more than we see today. And then once that occurs, all of this ice is reflecting sunlight away from Earth, so then the ice is continuing to accumulate. What finally occurs after all of this is that ice will eventually have either nearly covered the entire Earth or completely covered the entire Earth. The science is still continuing. The jury's still out on this, whether this was a complete glaciation event where ice covered the entire Earth or it just covered most of the Earth. But either way, we call this period in Earth history Snowball Earth. The formation of the Rhodinian supercontinent formed Snowball Earth. And it's another one of these terms I like because it tells you exactly what Earth looked like at this time. Earth was a snowball. Earth was either almost or completely covered in ice. So imagine what a setback that is for the evolution of life. Life was really thriving in all these shallow marine environments. You had these stromatolitic bacteria all over the place. And then ice is covering the planet. It's actually pretty remarkable that life was ever able to bounce back after that. But as we'll see, life really thrives on Earth in very mysterious ways and was eventually able to recover from the snowball event. So ice would have covered the globe or nearly covered the globe for possibly millions of years. But then what happens that gets us out of this snowball event is that the position of that supercontinent at the South Pole and all of those continental land masses all kind of teaming up right there would have created a lot of heat underneath the surface in the mantle. And that heat in the mantle would have eventually led to all this volcanic activity, splitting apart the supercontinent. And that already does something to change climate a little bit, just breaking up that supercontinent and allowing water to then flow back towards the South Pole again. That already breaks things up a little bit and breaks down the hold that ice has on our planet. But then after that, you also have all of this CO2 that's released into the atmosphere as a result of all of those volcanic eruptions. And that CO2 warms the atmosphere. So the process of getting out of snowball Earth and getting back into sort of the normal Earth and the normal sort of Cambrian period that's going to follow happened probably fairly rapidly over maybe hundreds of thousands to only a couple million years. So that was a really bad time for life, but in the wake of all of that, life is really going to start to thrive again. And life is going to eventually form macroscopic organisms. So again, prior to all of this, life was no bigger than a bacteria, right? All life was microscopic. But towards the very end of the Proterozoic, metazoans are going to become a little bit more common. That's going to be multicellular organisms. Eventually, these organisms are going to be big enough so that you could actually see them and we can see their fossil remains without the aid of a microscope. And so this last little section of life that's going to evolve right at the end of the Proterozoic and then evolve into the Cambrian fauna of the Phanerozoic, this is called the Ediacaran fauna. These were unknown for a really long time, so the beginning of the geologic time scale has essentially large-scale life occurring at the Cambrian. We thought that was the point in time when large-scale life really evolved. With the discovery of this Ediacaran fauna, this is going to kind of change the geologic timescale a little bit. As it turns out, large-scale life actually evolved before the beginning of the Phanerozoic, sort of making it where, the Phanerozoic might really need to eventually be expanded to encompass this section of time as well. So the Ediacaran fauna is mainly going to be soft-bodied organisms, and soft-bodied organisms don't fossilize very well. They are going to be very difficult to find good fossils of. But the reason why we call these the Ediacaran fossils is because there were really great deposits and great fossilization of this type of organism in the hills of southern Australia. And those are called the Ediacaran hills, and so therefore it's the Ediacaran fauna. These would have been soft-bodied organisms like jellyfish, worms, all of these very, very simple forms of animals that would later evolve into some of the more complex animals of the Paleozoic. So I've got lots of individual images of these and even some recreations of what the ocean floor would look like when just these types of organisms, all these sea fans and jellyfish and all these worms, all these soft-bodied organisms were really thriving in these environments. Later on, once we get into the Phanerozoic, we'll see how organisms that have hard bodies, they're going to form shells, they're going to eventually form things like bones and backbones, how that's going to really revolutionize biology. So that closes out the Proterozoic and the entire Precambrian, and so that's where we're going to close out today. In the next lecture, we're going to get into the Phanerozoic, and we're going to cover mainly just the Paleozoic era. Until next time, keep rocking.